Welcome to this talk, 7 reasons why your microservices should use event sourcing and CQRS, command query responsibility segregation. I've been doing this talk for a while, and it was hard to come up with 7 reasons. And I actually thought really seriously about changing one of the reasons, but it was like, oh, it's like, they're my children. I thought so hard about these 7 reasons, and I was like, which one do I kick out? But I didn't change it, but it's hard. There's a lot of reasons why this pattern of doing things is interesting. But before I get into the talk, I just have to say that I'm delighted to be here on Halloween. To me, I mean, I grew up on like Bela Lugosi and the Dracula movie and everything, and Romania and Transylvania to me is like the epicenter of Halloween, which is a pretty big deal. I know you guys think, well, oh, it's like that crazy American, holiday, but it is a big deal in the U.S. and where I live in Florida, but I grew up in Chicago, and which is up north, and it's a sacred holiday actually. My daughter, I have one daughter, and to her it's like one of the best holidays of the year. So to be here, it's like I was telling some of the folks yesterday, this is ground zero of Halloween as far as I'm concerned. You guys own Halloween. So for me to be here, it's just awesome. So I really appreciate the opportunity. So anyways, back to the talk. So for years now, and I know now, everybody's kind of at different stages of their journey, but there's been this massive what's called Modernizations journey that's occurring, where we're going from large and what's considered to be large and complex systems of monoliths to things like microservice systems, which are large and complex systems of microservices. But it's a different way of doing development of it's a fundamental change actually in the architecture of systems. But often the focus is on the code of the processing part of the application. But what I'm really going to be focusing on here is the persistence part. So there's really those 2 pieces to it. You're kind of taking monolithic code and breaking up the code into smaller, finer grain units of deployment. But there's also an evolution that we're trying to see happen, which is at the persistence level, which is often much harder to do. So I actually see event sourcing and CQRS as kind of an excuse for a way to break up your database, like a traditional relational database that's the foundational piece of a big monolithic system. This is a really significant different alternative for doing persistence. And it really is this segregation. There is a split. Segregation is split, right? And we're taking data and we're splitting it apart. And that's what I'll be showing you. Before I get into that, I wanted to, often when I talk to people at conferences or working with different people, different companies and so on, when user groups, whatever, we start talking about microservices. And I say, well, are you doing microservices? And maybe the answer is, oh yeah, we are. It's pretty cool. We're reading them, but they're maybe explaining what they're doing. So I try and kind of through the course of the conversation go, all right, well, there's kind of 3 characteristics that I think are interesting about microservices. So one is that, and this is the easy one, that one of the goals of going to finer grain units of code is that you're getting independently deployable units. So I grew up in a monolithic era, and I used to call our projects death marches, right? They'd be like 6-month projects, and we work, and we finally get everything ready, which was a total pain to get it all ready, and then we go through these horrible deployments into production, which were just torturous. It could be like whole weekends where we go into a deployment. So I was delighted to see patterns like microservices come along because wanted to have less friction in the actual deployment process. So independent deployability is usually one of the major first benefits you get with microservices. But then it gets more interesting. The next question is, Does the microservice own its own schema? And often this is where the answer is no, because what's happening is that the code is being broken up, but the data is not being broken up. And this is a form of coupling, meaning that if, say, you and I are on a microservice team, we have a microservice that we're responsible for, and we want to make some changes to the data structure, to the schemas, we probably have to talk to everybody else and negotiate with making those changes. That's a form of coupling. That slows us down. And I'm really kind of getting on this word friction. If you and I have to go and negotiate with everybody else, it's like, all right, we want to change the schema. Who's it going to impact? Have meetings and maybe have a coordinated deployment. So we lose some independent deployability as well. So the whole idea of having a microservice own its own schema is that it's loose coupling. It's self-contained. And then the final one is the only way to get to the data in a microservice is through its API. Now, it just so happens, this is way back in like 2002, this happened at Amazon. And it was like an email from Jeff Bezos to the company basically saying, you're going to do services like this. This is way before microservices. And part of the email was like, there's no backdooring to the data. If you own a service, the service owns its data. The only way to get to the data is through the API or the interface of the service. If you don't do this, you're fired. That was basically the email. And they've been doing that since 2002. So 3 basic characteristics. There's a lot of other characteristics of microservices, but I think these are 3 interesting ones. But when you propose breaking up the data, like I used to work at Hewlett Packard in IT, enterprise. We had database architects and so on, enterprise data, all that kind of stuff. And I left there before this really became more popular, but I'm imagining trying to have these conversations and say, well, we want to take this monolith and break up the code, but oh, you know what? We also want to break up the database. And it's like, no. It's not going to happen. You're crazy. Are you crazy? And you are crazy if you're proposing these types of things. So I don't know what you guys, if you're trying to do this, but if you may run it. This is where I often see people run into resistance is breaking up the data. So that's why I wanted to do the 7 reasons. But the 0th reason here is just kind of a quick description of what event sourcing and CQRS is. So let's take a look at that. So this is a diagram that I saw. I think it was there's some really good documentation from Microsoft that's been around for a while on event sourcing and CQRS. And they had a diagram similar to this where they showed kind of the general flow. So the flow is like this, that you say you have a client that's sending in a request to your service. The service treats that request as a command. And the command is, in general, it's like an intent to do something that hasn't happened yet, right? Like, please add this item to the shopping cart, right? So it hasn't happened yet. So the service gets that request, validates it if it's good to go. What it does then is it emits an event. An event is a historical, immutable fact. It's something that's happened in the past. Because as soon as you put a timestamp on something, time's moving on, and now that's a historical fact, okay? And the event is what's persisted. So say you're building a shopping cart. It's add item, add another item, update item, remove item. Each one of those is an event. You play all those events up, and you get the current state of the shopping cart. The interesting thing is things like that the shopping cart data now tells you what the shopping cart looks like right now. Say add item, update item, add a second item, remove the first item, so now there's 1 item in the cart. But we have all those events in the database, in the what's called the event store, or the event log. And we've got the data that we normally would throw away in a CRUD-based type of a system. I like to say with CRUD, you have update and delete. And when you do updates or when you do deletes, you're throwing away data. And in this day and age, when you're throwing away data, let's say every time you throw away some data, you make a data scientist cry, right? Because they want that data. In fact, I haven't really seen it much, but maybe a year or so ago, I saw this article that they termed it negative data, like remove item is negative data. meaning that it's not really, it's something that happened, but it doesn't impact, like the order doesn't contain that anymore because the customer added an item into the cart, then they removed it. But from a data analysis standpoint, that data is actually maybe even more interesting for analysis than the actual end result of a shopping cart. So these are some of the benefits that you get from using this event log. Now, so the events are just inserted. It's a simple database operation. Insert, insert, insert. Every time a command comes in, an event is created. The event's a historical fact. You just insert it into the event log. Then there's what's called the query side or the read side. Those events have to be propagated over from what's called the write side to the read side. So on the read side, you have data that's stored in a way that's optimal for the kinds of queries that the service would do. And this is interesting as well because now the data is the schemas for these query databases are being designed for the types of queries that the service does. So maybe the data is not normalized. Maybe the data is in a way that's, like there's some tables that are for one specific query, and there's some other tables for another specific query. As well as it might be that you have multiple data stores. Maybe there's some queries that are best served by relational database, and maybe other ones would be best served by Elasticsearch or Mongo or whatever. So you have more flexibility in the way you can store your data that's optimal for queries. So when a query comes in, say from a client, that goes to just this, it's a non-changing type of operation. We want to read some data, but it's being read from the query side. Okay, so there's what's called the write side that's handling the events coming in, real simple database operation, just inserting into an event store or event log. And there's the read side, which is data that's optimized for query. So we'll get back to some more of the characteristics of that, but that's kind of the general idea. So I'm a developer, I'm an architect, I'm not a domain-driven design person, but I like the kind of being on the receiving end of these, or a participant in these kinds of activities, the design activity. But the thing I really like about where this seems to be going is there's a real strong focus on events. And this is one, I did change this talk from what I did before. I used to just have domain-driven design and event storming. And event storming is a really interesting process where everybody gets together, the developers, the architects, the business sponsors, all the experts on the system, from the business side to the technical side. They all get together for a day or two, and they just think about the system as a bunch of events. What are the flows of events in the system? And they just write down events and post them up on a board. And the outcome of that exercise is things like an understanding of what's the flow of commands and events in the system. Maybe you're starting to get an idea of the candidates for microservices in the system. But the thing I added was event modeling. I recently came across, I think it's called eventmodeling.org. I really liked some of the things there because I think we're moving into this age of like this next decade. We're going to be starting 2020 next year, in a few months. So I'm saying it's like, okay, we're entering the third decade of this century. And I think that this third decade is going to be, for us, more of an event-driven type of thinking in the way we build systems. So event modeling is an interesting thing as well. But the flow of this is kind of like you're going from design down to kind of having an understanding of some of the flow of commands and events in the system and the microservices, which then transition into implementing services that are using event sourcing and CQRS. So I think there's a nice flow between the whole process, and that's, I think, a very powerful thing. So I'm going to be harping on this a lot, reduced service coupling. I mentioned it at the very beginning, but let's just walk through a little scenario. Very often when people implement microservice systems, the thinking is still kind of monolithic, where, say, you've got service 1 needs to get information from service 2. So easy, right? Some kind of a HTTP RESTful type of call. Service 2 does whatever it needs to do, and then sends back a response to service 1. And it's like, wow, that's easy to implement, right? No problem. But it's a form of remote procedure call, if you really think about it. And it's a form of coupling. When service 2 is down, I loved in the keynote, I am a big believer in this. When you're designing systems, you remove the word if from your vocabulary and you change it to when. When this service fails, what are you going to do? Not if. If is like, I maybe don't want to think about that right now. Let's put that off. But it's like when. If you say when service 2 goes down, how does that impact service 1? Well, in many cases, it means service 1 is down as well. So and it's kind of a big blast area. It gets even more interesting when you have two services that are interacting with each other and they're making changes. It's not just some kind of a query operation, but it's some kind of a change operation. So say service 1 is an order service. So when the user is building up a shopping cart, and at some point the user says, all right, I want to buy these items. So the order is placed, and the order, say, is in a new state. So that's state 1. And then service 1 says, all right, I need to check the customer credit. And that's in service 3. So service 3 does some kind of customer credit check. Maybe that does some kind of a state change. And by state change, I mean it's persisting some data somewhere. It's making a change to a database. And then service 3 goes, yep, here's my response. And service 1 goes, all right, thank you very much. Now I can change my order from, if the credit was approved, I can change the order to approved from new. If the order is rejected, or the credit's rejected, I can change the state of the order to rejected, something like that. But we've kind of gone through 3 state changes. Now, in a monolithic world, this was probably a nice, comfortable atomic transaction, and everything was cool. And then you move to a microservice world, and things get more interesting. But it's the same kind of thing. What will go wrong? When service 3 goes down, what does that mean? And actually, going down gets interesting because now you're in a distributed environment. You're talking over the wire, over the network, and just like what we saw with Burr in the keynote, and the network started acting up on them, right? Well, that happens in our distributed systems. So what do you do when service 1 can't talk to service 3 because there's a network break? The 2 services are up, but they can't communicate with each other. Gets even more interesting. What happens when service 3 maybe got the message, maybe acknowledged that it got the message, it was starting to do some work, and boom, it blew up before it could finish. Service 1 is waiting for the credit check to happen. Maybe service 3 did make a change, and then it's trying to send back a response, and it can't go back because the network is down. And maybe service 1 got the response. The point is that there's all kinds of failures that can happen here. What are you going to do when this happens? It's really easy to build a system where everything's working fine, but when you're in a distributed system, you got to think about all the things that are going to, get you pulled into production issues in the middle of a holiday weekend type of thing, which is not a fun place to be. So this is where the idea of kind of reducing the coupling comes in, and it starts actually in, say, the CQRS pattern, because we've got to propagate events from the write side to the read side. That's non-transactional. That's over the wire. It's 2 different databases, right? It's no 2-phase commit here, those types of things. So the approach that's commonly used is, this is kind of the Kafka pattern. If in Kafka, a consumer is pulling from Kafka, it's pulling messages from it. And this is the kind of the pattern that I'm showing here. There's some kind of thing that's reading, kind of offset driven, that's reading events. So it's trying to keep up. Our intuition often says that when we're building systems like this, where say there's service 1 is doing things that service 2 needs to know about, our intuition says, well, service 1 is responsible for sending the message. But the reality is, and this is really shown by the fundamental pattern of a consumer in Kafka, it's more of the pull approach is the better approach to use. And we'll look at that more as well. So it's kind of this pull by offset. It's happening between the write side and the read side, inside, but it's also an approach that's very usable between services. So I'm showing the same pattern here between service 1 and service 3. And it can even be, and we'll go into this more as well in a little bit, There's some interesting scenarios, even when, say, you have a service that's doing some work and then it's making a call to Kafka. And the question there is, what will go wrong? What are there vulnerabilities? And we'll take a look at that. So the whole idea is that it's trying to reduce the coupling between the services. And in this case, it's not so much for, say, the velocity of development. It's more for the reliability and trying to reduce the brittleness of the system. So let's move on. Reason 3: break the read versus write performance bottleneck. This has always been a trade-off where we're going to a single database and you're optimizing the database. If you optimize for reads, it comes at the expense of writes. If you optimize for writes, it comes at the expense of reads. So we're always trying to play this balancing game. And this is where splitting it apart, this is one of the intents, one of the major reasons for doing command query responsibility segregation is to split this apart. That the write side is extremely fast. You're just inserting, so the writes are just incredibly fast. And then the read side, it could be much more complex, but it's trying to keep up, but it might not always be keeping up. So the cost of this is eventual consistency, meaning that there's eventual consistency between the write side and the read side. Now, and this often is a concern when you start looking at this pattern. And there's a lot of material out here out in the world about this particular feature of command query responsibility segregation. But it's a solvable problem, and it's often interesting when you really say, all right, this is a feature of our system. How can we deal with it so that say the user doesn't see the eventual consistency? And I don't have enough time to go into the patterns, but people are solving this type of a problem. The next one is elevate the concurrency barrier. I don't know if you've ever run into this, but I have. I know it, and it's extremely painful. And what I mean by this is that the traffic on our sites varies a lot. It could be daily, that overnight the traffic is slow, and then during the day it peaks up. Or weekly, you could have maybe the weekends are busy, and during the week it's slow, or it's the reverse. During the week is busy, but the weekends are slow. But whatever. But the big killer often is the seasonal ones. Like the legendary Black Friday or Singles Day. Singles Day is November 11th. It's the biggest shopping day of the year. Singles Day is a big deal in China. And there's this massive seasonal spike in traffic. And the issue often is that you can scale your system. If you need more CPU capacity, we saw that earlier today. If you're running on something like Kafka, you can scale and do all that kind of stuff. But often the database may be struggling to scale. And the difficulty is that the way I kind of look at it, what I'm trying to show here is that you're hammering away at the database, and then you're kind of pushing it, and then you kind of hit the yellow zone. And the yellow zone is where you're pushing it, and the database is starting to push back, and it's starting to slow down. The really bad part is when you get those spikes, and you're pushing the database, and the database goes, I'm done. And I've been in those kind of situations where we've had systems where we're pushing the database, and the alarms are going off, and the DBAs are going, oh yeah, we'll fix it, and the DBAs don't fix it. And we're in this situation where the response time is, they kind of go up and up and up, and then they hit the yellow zone where the database is slowing down, then they hit the red zone, and then now response times really start to plummet. And they get really bad. This is a bad place to be. So one of the solutions for this is something like the Event Sourcing and CQRS persistence pattern. Because if you have a spike, the right side, all you're doing is inserts. I mean, it's like easily, and I've seen some tests, it's easily like an order of magnitude faster. But, of course, the cost is the read side is struggling to keep up when it might fall behind. It could fall behind, a fair amount. If you build your system to handle this pattern, you're in a good place. You've kind of really pushed that ceiling way up higher than where it was before. This is a big one for me, simplifying and hardening messaging. With messaging, and what I mean by messaging is like messaging between microservices or messaging within a distributed system. There's these three semantics of messaging. There's at most once, at least once, and exactly once. So I think of at most once as maybe once, which means some messages get delivered, some do not. And later today, I'm going to be doing another talk. I'll be talking about ACA. ACA is a system that is an actor system where actors asynchronously message each other, and it uses an at least once messaging pattern. But then for like messaging between microservices, what you really want is at least once. And what that means, though, is that once or more, meaning that every single message will be delivered. But the cost is that some messages will be delivered more than once. So the receiver has to be able to handle that. If it needs to be able to react properly when, not if, but when additional messages get sent. The same message gets sent again, some form of item potency. And there's kind of the exactly once, which is, I think of it as essentially once because it's kind of from the perspective of the producer or the consumer. On the consumer side, there's different strategies where the consumer has an exactly once way of doing things. So it doesn't have to worry about seeing duplicate messages. But usually it involves some form of filtering internal to how things are done. So Kafka, for example, has an exactly once pattern, which before they made the formal announcement and everybody knew they were working on it, there was a lot of controversy about it. They were getting beat up on Twitter and everything about it. But to their credit, when they came out with it, they were very clear. They did some really good blogs about how they implemented this. And basically, what they're doing is that the actual real consumer, upstream of the real consumer, somebody's filtering out duplicates. So dealing with the messaging, like I said earlier, often you think, all right, my service is producing this message or wants to send this message, so it's my responsibility to write the code to make sure the message gets sent. Well, that can get really fun because it's like, when the receiver, the consumer of the message isn't there, you maybe have some retry logic. And then the complexity starts to go up. Well, in retry logic, it's like, all right, you have to have some kind of way of knowing which messages haven't been sent yet so that you can keep retrying until the other service is coming up. And while you're in this kind of retry loop, say more and more things are happening in your service, so the backlog of messages that need to be sent is growing. So in effect, to harden this approach, you have to kind of build your own event log anyways. Because one of the things to consider is that you have service one that's pushing messages. It's running along, it's got pending messages trying to send to service two, but it can't, and then service one goes down. And when service one comes back up, it needs to pick up where it left off and resume retrying again. That's the real test. And then here's the one I wanted to mention about Kafka. That say you have a service where it's doing some kind of a database transaction. So that's step one, right? Transaction's done. It's committed. And it's like, all right, the next thing that the service needs to do is make a call to Kafka. So really easy to implement the code. But where's the brittleness in this flow? Where's the leak in the pipe here? The leak is that you've got this period of vulnerability between the time that the database transaction completed and you successfully deposited the message into Kafka. Because until you hear back from Kafka to say, yep, I got that message, you're vulnerable. So say you do the database transaction, and just before your code can make the call to Kafka, boom, it goes down, right? So now you've got a leak in your pipe. You've lost that message. How do you recover it? You have to think about these types of things. So this is where, again, I'm showing this pull pattern, that instead of having the producer push, have the consumer pull. And it's the semantics of this messaging is you're getting at least once. And this is the most common. We would love to have exactly once. It would make our lives so much simpler. But it's kind of like breaking the laws of physics and breaking the law, like going faster than the speed of light. It can't happen. The fascinating thing about distributed systems is that you really are dealing with things like the speed of light. Like the speed of light is too slow. I remember at HP, we consolidated down to 3 data centers. There was one in Atlanta, then there was a couple down south in Texas. And we actually ended up, I did a little like map, and I showed the number of milliseconds that it takes for the speed of light to get between Atlanta and Texas. It was something like 12 milliseconds. And we looked at it, it's like 12 milliseconds. You know, our normal database response times are like 2 or 3 or 4 milliseconds. We can't afford to be, trying to talk to a database that's 12 milliseconds away. These are the kinds of things that you get into when you get into distributed systems. And this pull pattern really works a lot. You know, it works for service to service, it works for service to Kafka, things like that. This is probably my favorite, well, the last two favorites, but I like this one. There's this pattern where, say, we've got a customer service that has information that these other 4 services need. You know, this is a common pattern. You know, a lot of other services want customer information. So yeah, you implement it, no problem. RESTful get your response back. So everything's cool. You set this up, system was working great. You're in production. One day, customer goes poof. Something's wrong. And it could be even worse. Maybe customer slows down. But in any case, say customer goes down. The end result is everything goes down. This is, again, a form of coupling. So a somewhat controversial approach, but I didn't invent it, but I like it. I like it a lot because I don't like brittle systems. I don't like systems that wake me up in the middle of the night with production issues, is this approach. So what customer is doing is that every time a change to a customer happens, it publishes an event. It's using something like an event-driven type of an approach. So the flow of events, like how often customers change, is extremely low ratio-wise compared to the number of times we read customer information. So the idea here is that customer just publishes an event. I just changed Hugh's profile, right? These other services are consumers of those events. So these other services actually have in their schema their own view of customer. Now, you look at this and go, okay, he's crazy. We're replicating data. That's been historically a very big no-no. We're relying on messaging. That historically has been a very big no-no. But the situation is that often our aversion to replicating data starts with cost, but that's changed so much. So recently, I grew up where data was extremely expensive to store, and now it's like free practically. I mean, we have almost, compared to what it was before, infinite amounts of data. It's very cheap. The bigger thing, I think, is the messaging. When you have a system that you know gives you at least once delivery, you don't have any leaky pipes, then this kind of pattern works. And the nice thing is that when customer goes down, remember, when customer goes down, these other services don't even care. They just keep running. That's where you want to be. This is a form of loose coupling. So the final one, and I come from the enterprise space, so this is a big one for me, is graduate from the IT nursery. And what do I mean by this? Is that I hate governance. I grew up in a highly governed environment where we had to beg for servers. We had to beg for database changes. We had to go through all these processes. I just recently worked with a customer most of last year, 2018, and they were moving to a Kafka environment. They were trying to modernize their approaches, but they had Kubernetes, they had Kafka, and I remember hearing or seeing meetings where they were 20 people were in a meeting talking about the naming convention for topics. And they had to fill out forms to get topics and stuff like that. It's like, wait a minute, come on, this is the third decade of this century, and we're still doing these kinds of things. So my rant is, the idea is that you're trying to get this loose coupling. You're trying to remove the friction. You learn through your mistakes, and your mistakes are by design smaller. You're going into finer grained units of building systems, which means you should have more freedom to learn. And you're going to learn really fast. But it's not like you blow up, you screw up a big old monolith. It might be that you screw up at maybe the initial version because the team is new to microservices and they do something that when they're experienced they wouldn't do. But they'll learn, and so they don't need a lot of hand-holding. They don't need to be in a nursery, I think, to grow. Because the real goal, I think, is extremely important, is you need to increase your velocity of development of features. And everything that stands in your way of doing that, again, is friction. And governance, to me, is a form of major friction. I've just spent way too much time, and I've seen other teams spend vast amount of time filling out forms and going to governance meetings and things like that. It drives me crazy. So I added it to my list. So kind of wrapping up, people, I love this statement. People are very open-minded to new things, as long as they're exactly like the old ones. And it's like, we cannot afford to be like this. This is against our human nature. We don't like change, but in our businesses change. Our business, and boy, I don't know how long you guys have been in the business, but if you think like the last few years have been interesting, I'm really looking forward to the 2020s. I think the 2020s are going to be amazing. And wow, I think the changes that are going to happen are going to be massive. And the ones that are going to take advantage of it are the ones that are going to have the nimble minds that are not afraid of change, the ones that are ready to move forward. And I think there's way too many companies that are almost paralyzed with fear. And and their competitors are, if they have competitors that are not, you're going to be in a world of hurt if you're in an organization that's paralyzed with fear and fear of change. And you have to embrace this kind of change. So those are the 7 reasons. One I'll just add real quick. I think I've got a few minutes. The one I was thinking about adding to this, maybe it's like an 8th reason, is stateless versus stateful. And in fact, I'll be talking about a stateful microservice way of doing things this afternoon. But the stateless pattern is almost like the no-brainer. Yeah, you build stateless systems, right? And it's like, yeah, because they're simple. There's a lot of good reasons for doing it, and I'm not debating that. But we have to have an understanding that there's a cost associated with it. And the way I kind of think about it is that with a stateless system, it's just like serverless. They always say with serverless, oh yeah, there's not serverless. Like, yeah, we knew that. But every paper I read, every talk, it's like, yeah, serverless still has service. Like, okay, I know. But with stateless, there's still state. So what happens is the service has to retrieve the state from the database, make some changes to it, and then push the state changes down to the database and then kind of throw it away. So that's fine because it's simple to implement and it scales, like where you can scale the service, but you're putting a lot of strain on the database. You're lifting everything out of the database, making some changes and pushing it back into the database. This pattern is one where we're trying to break that pattern. So the idea is that with a stateful type of service, you pull the state out of the event log, recover the state at, say, the order, and then you keep the state. And then now commands are just coming into the state, and the only thing that's being emitted to the database while you're maintaining state are the new events. So the I/O, strain on the database is significantly reduced. So I'm not saying everything should be drop stateless and go to stateful. I'm just saying that in situations when you want to have an opportunity to optimize the performance or take maybe some of the strain off of your database, then this is a pattern that facilitates that. So maybe that's my 8th reason. Maybe I should change this to 8 reasons. That's the material I had. I appreciate your time. I'll be around today. Like I said, I'm here for another talk this afternoon, and I'd love to chat with you if you have any questions. Thank you very much.